All right, we are going to revisit inverse functions in the context of polynomials and rational functions. The interesting thing is most polynomials you're not going to be able to find an inverse for. Why is that? Well, remember when we talked about inverses, a function must be one-to-one in order to have an inverse, and most polynomials are not. So most of the things we're going to talk about here are things we already talked about in chapter 1 when we talked about inverse functions. But it can be a complicated topic, so it's good to revisit it. All right, so let's just think about the definition of an inverse function. We can verify two functions are inverses of one another if we compose them and out pops x. Right? We can compose them in either direction, g of f of x or f of g of x. If both of those equal x, then we've got inverses. F and g are inverses. So one kind of thing we could do is show that this function and that function are inverses as long as we restrict the domains appropriately, right? We can't have x equals 0 or -1. So just as a quick review of composition, f inverse of f of x, f inverse, this should have a -1 right here. We're just plugging 1 over x plus 1 in for x. F inverse of this function. Everywhere there's an x, we plug in 1 over x plus 1. This we can simplify to just be x plus 1. That ones cancel and we just get x. Right, over here, f of f inverse is going to be f of 1 over x minus 1. We plug that into our function. These cancel. We're just left with 1 over x, which is just x. You guys did problems like both of these for your homework and on the first test. All right, what if we have this function? It's a cubic. Are cubic functions one-to-one? Yes, we can think about our toolkit function, right? It goes like this. This means it's going to be vertically stretched a little bit, and this is shifted. But that's not going to change that it's one-to-one. So we can just find this like we'd find any other inverse. So how do we do that? We say y equals this. We switch all our x's and y's. We solve for y. So we bring the 1 over, and we divide by 5, and then we take the cube root, and we get the cube root of x minus 1 over 5. And that's what we've got, right? Our original function is this blue one. It's a cubic that's stretched and shifted. And remember that inverses reflect across the line y equals x. So this red graph is going to be this function, the cube root of x minus 1 over 5. All right, but sometimes it's not so easy. Sometimes we have to restrict the domain, right? If a function is not one-to-one, it cannot have an inverse. So if we restrict the domain of the function so that it becomes one-to-one, creating a new function, this new function can have an inverse. So sometimes with polynomials, with many polynomials, that's what we've got to do. So what if we started with x minus 4 squared? X minus 4 squared. In part A, they restrict the domain to greater than or equal to 4. Over here, they restrict it to x less than or equal to 4. Both of those will work because what is this function? This is a quadratic, so it's a parabola that's been shifted to the right by 4, right? So its vertex used to be at 0, and now it's at 4. And so this is going to be where the parabola is increasing, and this is going to be where the parabola is decreasing. Both of those are one-to-one, so yep, we can find the inverse. So they kind of show us here, right? Here is x minus 4 squared restricted to x greater than or equal to 4. And here's the other half if x is less than or equal to 4. Right? If we put them together, we would have a parabola. All right, so let's find the inverse. We say y equals x minus 4 squared. We switch the x's and y's. Solve for y, so we take the square root of x. And since we do that ourselves, we have to say plus or minus the square root of x, because we took the square root ourselves. So we have to say plus or minus. And then we add 4. So we get y equals 4 plus or minus the square root of x. So how do we know which of these we're going to use for this? Okay, well, let's think. Our inputs here have to be greater than 4, in which case our outputs are going to be, so our domain is greater than 4. Our range is 0 to infinity, right? So that works out here. Our range, our domain, so remember our domain and range switch for inverse functions. So our domain is all positive numbers, or all non-negative numbers. That's right. For part A, we need our domain was greater than or equal to 4. So here we need our range to be greater than or equal to 4. So for part A, we're going to take 4 plus square root of x. For part B, it's the opposite. We need our range to be less than or equal to 4. So it's going to be 4 minus the square root of x. So this kind of restates that. So if that was confusing, you could pause this and read these two explanations. And we can kind of see what the graphs are going to look like. Right here, if this is our blue function reflected across that line, it's going to be 4 plus the square root of x. That original square root of x function shifted up by 4. Here was a function restricted to fx less than or equal to 4. Reflected, it looks like this. And yeah, this graph is going to be the original square root of x function reflected across the x-axis and then shifted up by 4, which is what we get here with the red graph. All right, so here we've got something very similar. We have a quadratic shifted to the right by 2 and shifted down by 3. It says restrict the domain and then find the inverse. So we can choose either half of this quadratic. Let's restrict it. We usually restrict it to the positive increasing half. Okay, so let's restrict it to x greater than or equal to 2, right? So we had original parabola. We shifted it to the right by 2 and down by 3. And now we're going to take the right half of it. So it's going to be x greater than or equal to 2. And now we just do what we always do. Set it equal to y, switch the x's and y's, solve for y. We take a square root ourselves, so we have to have plus or minus. So our final function is 2 plus or minus this, although is this a function? It is not, right? This is a sideways parabola. So we are going to have to take one or the other of these, 2 plus this or 2 minus that. How do we decide which it is? Well, our original domain was x greater than or equal to 2. So we need that to be our range. We need our range to be greater than or equal to 2. So we're going to take 2 plus square root of x plus 3. Right? And here's what the graph looks like. Here's the right half of that parabola. Here is the square root function shifted left by 3 and up by 2. Right? And reflected across the line y equals x. All right, how about this one? We're starting not with a quadratic, but with a radical. Restrict the domain and find the inverse of this function. Well, the original function has range f greater than or equal to 0. Is that true? The range is greater than or equal to 0, yes. The domain is going to be has to be positive, right? So it's going to be x greater than or equal to 4. The range is going to be greater than or equal to 0. We go through our normal procedure. Replace f of x with y, switch x and y, solve for y, so we square both sides, and we get y equals x squared plus 4. Okay? So our original range was this. So what does our domain have to be here? Our domain has to be x greater than 0. Okay, we're only going to take half of this parabola, right? This parabola is just shifted up by 4. The range of our original function has to match the domain of our inverse function. So we're going to take just this half of that, the inverse function, okay, to make it an actual invertible function. And once again, we can see that the graphs reflect again across each other across y equals x. Okay, so this is a little bit of a stretch of a section because, like I said, most polynomials are not invertible because they're not one-to-one. So quadratics and square roots or cubics and cube roots are usually as much as we do with inverses when we're talking about polynomial functions.